welcome back to Topics in Statics. This time we're going to talk about internal effects within beams. This is particularly important if you want to design a beam, a structural member. How do you know how to design it? You have to know what the internal loading is going to be in order to know what to make it out of, what shape it needs to be, etc. The basic idea, we do this by essentially doing the method of sections on the beam and looking at the beam where I cut it and looking at what those effects are. So here I've got a cantilevered beam with two external forces on it, two external loads. And I want to know what are the internal effects at point B. So I'm going to slice it at B and look at two different things. So by looking at the left-hand side on the bottom picture, right, I get these forces at B that have to be there. And what are all these forces that I've got? VB, NB, MB, what are all those things? These internal loadings, if you get a force that acts perpendicular to where I sectioned it, that's called a normal force. If I get a force that's tangent to where I sectioned it, that's called a shear force. Right, both of those forces act to prevent translation of the beam. Then I also get a couple moment that's developed in the section, and that's called the bending moment. That tends to make the beam bend. In 3D, there's two different shear force components and two different bending moment components. And then there's a third moment called a torsional moment, which makes the whole thing twist. Imagine trying to grab that beam with both hands and twist your hands in opposite directions. And you get a twisting motion of the beam. That's a torsional moment. We're only going to work a little bit with internal loadings, and we're only going to do them in 2D. Now there's a sign convention for all these loadings, and it depends on whether I'm looking at the left-hand side or the right-hand side of where I sectioned it. And so the normal force produces a tension, then it's positive. If the shear force produces a clockwise rotation of the segment I'm looking at, then it's positive. If the bending moment causes the segment to bend concave up, then it's positive. Yeah, that's very confusing. So the basic idea is take an imaginary cut where you need to determine the internal forces, decide which side you're going to analyze, the left side or the right side. Right? Figure out any support loadings you need, support reactions you're going to need, etc. Draw the free body diagram, show the N, V, and M loads at the cut, and apply equations of equilibrium. So here's an example. I've got this distributed load over here on the left-hand end of this beam, and I want to know what are the internal reactions at point C. So I'm going to imagine cutting it at point C. So now which side do I want to work on? The left-hand side or the right-hand side? Well, to me, it's going to be much easier to just ignore that distributed load and look at the section from B to C. So the right-hand side. So the first thing I need to do is figure out the support reactions at B. So we draw a free body diagram of the entire structure. Now that distributed load is equivalent to a force of how much? 18 kip. So this is 18 kilopounds, and that's going to be located 30 feet from the left. Then I get a support reaction here, AY. I get a support reaction here. I get a BX, I get a BY. So now I can do this very easily. Let's not do it in red. I get the sum of the forces. X equals 0, so BX equals 0. So far, so good. Then I do the sum of the forces. Y equals Then we do the sum of the moments. Right, I'm going to do the moments about A. So I get 18 kip times 3 feet. That's going to make it rotate counterclockwise. Then I'm also going to get by times 9 feet. That's going to make it rotate counterclockwise. And all that has to add up to be 0. So it looks like my by is the wrong direction. So I get by is minus 6 kip, or it's 6 kip down. Okay, so now let's see if we can clear up a little space here. So now we're going to do a section. We're going to section it, and we're going to look at the right-hand side. So my forces over here on the right-hand side, I get 6 kip down. I'd get a normal at C. I'd get a shear force at C. I'd get a moment at C. So we can tell right away, if we do the sum of the forces in the x direction, I can tell that the normal component at C is 0. With this loading, I don't get any normal component. There's no tension or compression in that beam. I can also do the sum of the forces in the y direction. That's equal to 0, which tells me that minus VC minus 6 is equal to 0. So VC is minus 6 kip, which means it points up. And then we do the sum of the moments about C. So the moments about C, I get 6 kip times 4.5 feet. That's going to make it rotate clockwise. And that has to be equal to my moment about C that I calculated, that I put on the figure. So 6 times 4.5, that's going to give me MC is 27 kip feet. And so there's my internal reactions. There's this, and there's this. So let's look at another problem, one that's slightly more complicated. I've got a beam loaded as shown. There's a pulley and cable, all kinds of good stuff. We want to find the internal loading at point C. So I'm probably going to want to work the left-hand side of this. I don't want to include all that pulley and stuff when I start analyzing the internal structure. So I need to find the support reactions at A. So the entire beam includes that pulley. The forces acting on it now are going to be, I've got a 400 Newton force here. I've got By there. got AY, I've got AX. I think that's everything. That's all the external forces acting on this. So from the sum of the forces in the x direction, that tells me that AX is minus 400 newtons. It's pointing to the left. Then I do the sum of the moments about B equals 0. Sum of the moments about B. So I get AY times, how far is that? 5 meters. That's going to make it rotate clockwise. Right, then I'm also going to get this 400 Newton force times 1 meter. That also makes it rotate clockwise. And that's it. I solve for AY and I get minus 96 newtons. So it points down. So AX points to the left and AY points down. So give ourselves a little bit more room to work this problem. So now we're going to section it. So I'm going to look at the section from A to C. So at A, I've got two forces. I've got this force pointing down. This is AY. I got this force pointing left. That's AX. So I'm going to get a shear force. I get a normal force. And I'm going to get a moment. So now my equations of equilibrium say that the sum of the forces x equals 0. So that tells me that the shear force or the normal force is 400 newtons. Points to the right. Sum of the forces in the y direction equals 0. That tells me that BC is minus 96 newtons, which means it points up. And the sum of the moments about C equals 0, which is that 96 Newton force times 1.5 meters plus this moment has to be equal to 0. So the moment at C has to be minus 144 Newton meters, which means it goes clockwise. Next time we'll talk about writing these in form of equations and diagrams. Until then, keep on working problems.